It's said that Mirigan the hunter once tried to spear the snake Gurungutch, who lived in a deep water hole. The snake escaped by burrowing into the mountains, creating a labyrinth of caves and rivers, those that we know today as the Jenolan caves in the Blue Mountains west of Sydney. Aborigines of old avoided the caves, believing them inhabited by the spirit of the snake. Most of the spirits that inhabit Jenolan these days are those of paying tourists who daily pass through the dozen or so display caves. This year, almost 300,000 people will visit Jenolan to see some of the world's best cave formations. But away from the caves that are open to the public, deeper within the 42 kilometres of caves that make up the Jenolan system, scientists are excitedly at work on one particular kind of cave formation that the average tourist wouldn't give a second glance. The formations are in a secluded cave, well away from the tourist crowd. Dr. Julia James leads the way. She's an inorganic chemist at Sydney University, but her first love is caving.
Right, now we've got to get through this gate. This is to keep out the general public. They haven't been allowed in here since 1934.
It doesn't look like it's on the tourist route.
No, you're coming through here.
Within this cave, Julia James believes, there's a detailed chart of the Jenolan area's climatic history. The chart goes back many thousands of years, and it's locked inside these unusual structures.
We found this curious thing, which we now call a stromatolitic stalagmite. And we'd found it first at Wombian, but then my colleague came back from Jenolan and said, I found a whole cave full of the things. Isn't this great? So we've started to study them here.
Did you catch the wombat last night?
Yes, we got it out from under the house.
What time did you get...
Julia James's colleagues aren't cave scientists by training, but they share her passion for caves, and in particular for stromatolites. Stromatolite simply means layered rock. But these lobster-shaped formations are much more involved than that. They might look like close cousins of your straight up and down stalagmite, but they're not just made by calcium carbonate and water. These rocks are built by a living organism called cyanobacteria, as biologist Dr. Guy Cox explains.
Well, yes, it is a stalagmite, there's no doubt about that, but the way it's formed is rather different, because we've got here this green colour from the cyanobacteria, things which used to be called blue-green algae, that they're not really algae, they're a sort of bacteria, they're one of the most primitive forms of life on Earth, and they've been responsible for forming a substantial part, at least, of this stalagmite.
All stromatolites that have been found so far have been growing in water, like these on the Western Australian coast. That made the Jenolan discovery all the more startling.
When I came here on a trip doing an environmental impact statement, and we found the whole place just full of them, we were absolutely flabbergasted. The very first signs of life that are found in the fossil record are stromatolites, and here we've found some in a cave at Jenolan. Modern-day stromatolites are extremely rare anywhere, and in a cave they're quite unique.
That's all very well, but how do they tell us about past climates? Well, that relates to how stromatolites are formed. Stalagmites occur when rainwater drops through the limestone above onto one spot, slowly building a tower of calcium carbonate. But stromatolites, as we know, are built by cyanobacteria, and cyanobacteria need light and water to live. So just how many cyanobacteria are active at any one time over the years depends on how much light and how much water enters the cave. That means recording external conditions at a weather station near the cave to see how rainfall, wind and temperature affect the cave's own microclimate.
Take this photo cell and hold it up near where Julia is holding hers.
Yeah.
These photo cells, for instance, record just how much light is reaching different parts of the stromatolite.
You've got to point it towards the light.
Right.
It's like the Statue of Liberty.
Yeah, you're taller than me.
Where there's plenty of light and plenty of water, the cyanobacteria are very concentrated. They react chemically with the calcium carbonate to produce smooth growth. Where there's less light and water, there are less cyanobacteria, and this knobbly, coral-like surface results. Those different surface textures are the key to interpreting the stromatolite's information about past climates.
250.
When we cut open one of these, we can see inside records of both types of growth. We can see evidence of this sort of coralline growth, which indicates that conditions were dry and evaporation was taking place, and we can find smooth layers of calcite, which indicate that there was light and water and the cyanobacteria were growing and precipitating calcite.
By cutting the lobster in half, you can see the layers that have been deposited over the years. They show the same two distinct textures, so if you date the layers, you can tell what climate existed when.
The layers we've dated down here are 20,000 years old. We believe, from the evidence that we have here, that the climate was somewhat wetter than it is now, that our cyanobacteria were very active. Then we go on up, and you notice it now becomes white, and the structure becomes coralline. Here we believe the climate got much drier, and we were getting pure calcium carbonate depositing, and the cyanobacteria were less active. Something went awry around here, which is roughly 10,000 years ago, a bit less, and you can see that we've got a very heavy layer of detrital material, which probably means at that time it was very dry. It's just like a time chart. Yeah. It's very exciting, the way it tells us about the past climates. The oldest one we've got so far, and the one we've been able to date, is 20,000 years old. But we believe one as large as this will be much older. Now, we can't take a speleothem from a cave and sort of cart it away and section it in the lab. We'd have to be very careful if we sampled one of these very large ones. So we're working on much more samples in the laboratory.
Laboratory analysis will give a much more detailed picture of past conditions, and the techniques being pioneered here may well be applied to quite different geographical areas, extending our global understanding of climate change.
Does it go?
This is probably the only place that stromatolitic stalagmites are being studied. They were protected very early on in Australia's history. And we need to keep them that way, not only for scientific study, but for everybody.
And that's Quantum for this week. Next week, a